Hi everybody, it's Miss Austin and I'm going to be doing the Unit 4 Lesson 17 practice problems. Number 1, the relationship between a bacteria population in thousands and time d in days, since it was measured to be 1,000, can be represented by the equation d equals log base 2 of p. So they've written it as a logarithmic function, and we're going to select all the statements are true. Now, I think it's also helpful because this is sort of a new way to think about it, to rewrite it as an exponential. So that's 2 to the d equals p. 2 to the d equals p. That's the equivalent logarithmic expression. So here we go. It says each day the bacteria population grows by a factor of 2. There's your base. That means I'm multiplying by 2 every day. Yes. The equation p equals 2 to the d also defines the relationship between the population in thousands and time in days. Yes, we had already done that. C, the population reaches 7,000 after log base 2 of 7,000 days. Log base 2, well, we're doing d is in thousands, so no, because that would be log base 2 of 7 would give us 7,000, not 7,000, because p is in thousands. No. Letter D, the expression log base 2 of 10 tells us when the population reaches 10,000. Yes, this number gives us the population, or the answer to this would give us how many days it would take. Are we doing days? Yes. For the bacteria population to get to 10,000, because this is in thousands. Yes. The equation d equals log base 2 of p represents a logarithmic function. Yes, it's written as a log. On letter F, the equation 7 equals log base 2 of 128 tells us that the population reaches 128,000 in 7 days. Yes, this 2 to the d, 7 days, is the population. Here's a graph of a logarithmic function. What is the base of the logarithm? So what I would do for this is I would try to find a point that I can clearly see and see if I can figure out. So I can tell this point looks good. And on a logarithm, right, so I have y equals log of x. And I've got the point here, 1,003. So this is the power. So some number to the third power is 1,000, right? 3 equals log 1,000. 10 to the third power is 1,000. So this is base 10, log base 10. Because 10 to the third power is 1,000, and that was a point right there on my graph, 1,003. Log base 10. Number 3. Match each equation with a graph that represents it. So again, I'm going to use the strategy. I'm going to try to find a point that I can reason with and then kind of work backwards. And I'm also going to rewrite these as exponentials. I'm just going to say y for now on these. So 2 to the y is x, 10 to the y is x, 5 to the y is x, and ln means e to the y equals x, right? That's log base e of x. All right, so now let's go see if I can find a point. This is a nice point, 102. And just like I did on the previous problem, right? What number to the second power is 100? That'd be this one right here. 10 to the second power is 100. So this one, number 2, is letter D. And then I also noticed something, I mean, maybe because I'm a math teacher, but 10 is the biggest base out of all of these, and it's the lowest graph. Because these are the inverse of an exponential, right? Normally, if I had 10 to the x, if I graphed this, it would be the fastest growing, right? It'd be the, and so I believe these are going to be reversed. So this is going to be the 10, and then the next biggest number is 5. That's going to be C. So 5 to the x is going to be C. And I could check, let's check a point on here. C, that looks like 150. Well, is it a little bit more than one? It's a little bit more than 150. That looks like about 125.3. That pretty much confirms that. 5 to the third is 125. Yep. So we had 10, 5. Now that's 2.7. So this one should be B. Let's maybe pick a point here and see if it lines up. I've got 406. Let's see if that works. I'm going to just test that on my calculator. E to the 6th power. Yeah, about 400. It's not perfect. And therefore, the smallest base was 2. That would be my letter A, the number 1. All right. Number 4. The graph represents the cost of a medical treatment in dollars as a function of time, D, in decades since 1978. The expression 150 times 1.35 to the third represents the cost of medical treatment sometime after 1978. Which year does it represent? Well, first of all, we've got to figure out how was this defined. So this was back from Unit 4, Lesson 5. So 150 to 202.50. Let's see, is that where they got the 202.25 divided by 150? That's where they got the 1.35. And that is for a half of a decade. So this is for every 5 years. So if they have a 3 there, right? So this was defined for a half of a decade, and they've got a 3 there. So that's 3 half decades, which is what? Half decade is 5 years, another half decade, and another half decade. 3 of those is a total of 15 years. Well, when did this problem start? 1978. 1978 plus 15 years is 1993. Number 5. The equation A of W equals 180 times E to the 0.01 W represents the area in square centimeters of a wall covered by mold as a function of W, time in weeks since the area was measured. Explain or show that we can approximate the area covered by mold in week 8 by multiplying A of 7 by 1.01. So even though this is written with E because it's continual growth, right? I can tell that the growth rate is 1%, right? So that means that 1% is 1.01 as I move from one year to the next. So I should be able to, if I have the answer to the 7th year, I should be able to just multiply by this to get the 8th year. And it'll be approximate. So let's just see. So if I take the 7th year, 180 times E to the 0.01 times 7. Let's see what I get. 180 times E to the 0.01 times 7. So I get 193.05. This is in weeks. Okay, so now the next week it should grow by 1%. So I should be able to just take that answer and multiply it by a growth of 1%, right? I need the 1 to carry the amount from week 7. So now I've got 193.05 times 1.01, so about 194.98 square centimeters. Now let's see how close that is if I just would have put 8 in here. 180 times E to the 0.01 times 8 weeks. 180 times E to the 0.01 times 8 weeks. 194.99. See how close that is? All right. Number 6, solve each equation without using a calculator. So we're going to try to do these mentally. Some solutions will need to be expressed using logs. So I know 10 to the first power makes 10. So I need this expression to be equal to the number 1. Some of you can just look at that and know it's a 4. I can actually solve it. N needs to be 4. Put a 4 in there. 4 minus 3 is 1. 10 to the first is 10. Okay. I'd like this to be written where it's just a power of 10 without this. So I'm going to get rid of this multiply by 1/2, I'm going to multiply by the reciprocal. That's the way I get rid of fractions. Right, 10 to the x equals 0.05 times 2 is 0.1. I like to think of that as a fraction. Because then I can see, hey, wait a sec, 10 to the first is 10. Why is it on the bottom? Because that needs to be a -1. And then you can go back and check and type it into the original. All right, what do we have here? 10 to the what makes 100. I need that power to be 2. So this expression, I know 10 squared makes that. So 1/3 t needs to be 2. Some people can figure that out in their heads. I'll solve it mathematically. To get rid of 1/3, I'm going to multiply by 3 over 1. Whatever I do to one side, I do to the other. The 1's sort of not important. 6. 1/3 of 6 is 2. 10 squared is 100. All right, now this last one, 10 to the what is 48? I don't know that one off the top of my head. This one I'm going to write as a log. Log base 10 of 48 equals 2x. How would I get x alone? Divide both sides by 2. X is going to be whatever log. I'm going to drop the 10 because if no base is there, it's assumed to be 10. Log base 48 of 2. And you could type that into your calculator if you wanted. Last one, number 7. Looks like we're going to have to look at Desmos maybe. The population of Mali can be represented by M of t equals 17 times e to the 0.03 t. The population of Saudi Arabia can be represented by G of t equals, S of t equals 31 times e to the 0.015 t. In both models, t represents years since 2014, and the population is measured in millions. Which had a higher population in 2014? Well, that's when it started. No work required. Look at the equations. The A value is the starting amount, 17 or 31. Saudi Arabia, 31 million. Mali only had 17 million. Which country had a higher growth rate? No work required. You just look at what E is being raised to. This one, right, Mali, that stands for 3%, and that stands for 1.5%. This had a 3%, and Saudi Arabia only had 1.5%. So this guy. Using graphing technology, graph them on the same axes, and then it says, do they intersect? If so, estimate it. Let's see if Miss Austin can share her screen here. Hopefully. Oh, come on. Okay, so I'm going to type in the first country's equation, which was 17 e to the 0.03x. And then the other equation was 31 e to the 0.015x. Now I can't really see these, so I'm going to go adjust my window. I mean, the starting population is 17 for one of them and 31. So I'm going to go up to like 50. Maybe I'll go to 100 because I can. Okay, so that's what it looks like. Now it says, do they ever meet? So I'm just scrolling along here, and boom, looks like they do. 40 years, wait, decades. Is this decades? And 40, nope, years. 40 years from 2014, both the populations will be about 56.25 million. Okay, so now I'm going to go over here, back to my paper. And so we had, 17,000, which was growing, and then 31,000, which was going a little bit slower. So eventually that point was, maybe forgot what it was. Miss Austin. Let's go back and look. Forty years and 56. I'm just estimating. 40, 56. So in 40 years from 2014, so that'd be what, 2054? Both will have a population of approximately 56. Okay. All right. Hope that helped. I'll see you soon.